Are the oxalates in our food really the primary issue? What about the oxalates that our own bodies produce? We'll be answering these questions in today's episode of the Energy Balance Podcast, the podcast where we explore health and nutrition from the bioenergetic view and teach you how to maximize your cellular energy to maximize your health. Today's episode is part 2 of our oxalate series, and in today's episode, we'll be digging into how much oxalate your body produces and how it compares to the amount that you consume in your diet. We'll discuss whether you need to be concerned about vitamin C, hydroxyproline, and glycine converting to oxalates. We'll also go over how you can reduce the amount of oxalates your body produces, which nutrients decrease oxalate production, and how metabolic dysfunction affects oxalate production. As always, to check out the show notes where I'll link to the studies, articles, and anything else that we reference throughout today's episode, head over to jfeldmanwellness.com/podcast. And with that, let's get started. All right. So in the last episode, we talked a lot about the exogenous oxalates, the oxalates that are in the foods that we consume. And we'll talk later on in the series about the details there and how we can construct a diet that minimizes oxalate exposure, but without the cost and what that looks like and everything there. But a huge part of the oxalate conversation is not just the oxalates that are in the food that we absorb through our gut, but rather the amount of oxalates that our bodies actually produce. And so that's what we'll be focusing on today. There's a lot to dig into. And we'll start by just looking at this figure here that kind of gives us a good broad overview of the different sources of oxalates and where they're coming from, how they all kind of interact with our physiology. And what you can see here, of course, is that there's oxalates in certain foods, the exogenous oxalates that make their way into the intestines. And then we don't absorb the insoluble oxalate so much, as we talked about in that last episode. But the soluble oxalates are much more absorbable, and we can absorb those into our bloodstream, and then they can have effects all throughout the body. We have to clear them out in the kidney. And then the other side of the equation is the endogenously produced oxalates, which are generally produced at the liver. That's the primary site of production. And there's a number of different pathways that are involved here that we'll discuss, and what regulates those and how we can reduce the amount of oxalates that our liver is producing and what kinds of things might increase it that we want to be aware of. So that'll really be the focus today. And Mike, I'll let you jump in and feel free to share anything on the overview side, or if not, we can dig into some of the details here about the different genetic factors that can affect oxalate production and then the factors that are important for the vast majority of the population that doesn't have those genetic issues.
I think the biggest thing on my end that I want to mention here is that the large portion of the oxalate conversation has been centered around the idea of exogenous oxalates. And the thing is that exogenous oxalates on average are likely to not be so exogenous meaning oxalates coming from food or other sources that your body is not producing by itself. But exogenous oxalates are actually on average not going to be the major sources of oxalates coming in or that the body's exposed to. The major source is going to mostly be endogenous oxalate production. And so it's kind of interesting to me that there's so much focus on this exogenous sources, these sources taken in from the diet, and there hasn't been as much discussion beyond vitamin C as being the endogenous production or the endogenous sources. And the reason why this is a big deal is because I think most people who are having issues with oxalates are not having the issues with oxalates because of too much consumption. They're having issues with oxalates because of changes in metabolism of oxalates in their body. And so we want to really dive in and talk about what is going on with oxalate metabolism. What are the factors that can affect oxalate metabolism inside the body? Because I think this is where the biggest issues come from. Because the people who are having issues, like for example, Sally Norton is describing that when she was very young, she was having issues with oxalates. Is this because oxalates are a problem for everyone? Or is this because Sally Norton has potentially some issues with oxalate metabolism in her body that led her to be more susceptible to the effects of oxalates than other people are? Maybe an excretion issue, maybe a production issue, maybe an issue with citrate production, things like this that would make her more susceptible, and therefore she would have to lower her intake overall because of her susceptibility. But for the vast majority of people, the dietary oxalates that we talked about in the previous episode, I don't think are going to be the major concern. It's really going to be what's going on to a large extent endogenously and how do we affect those things. And then also what amount of oxalate is even going to be a problem from endogenous production. These are things that we really want to hone in on to start to understand the full picture for oxalates.
Yeah, absolutely. That's a great point. It's very much under-acknowledged and under-focused on. And as you're saying, probably deserves more of the focus. Obviously, there are some, small things from the diet that can make a really big difference in terms of oxalate exposure. And so we want to be aware of those. But at the same time, as you're saying, the endogenous side is massively important. And especially in the people who are dealing with more chronic issues, especially if you're not somebody who was on a vegan diet, juicing spinach, consuming massive amounts of dietary oxalates, then that's probably not going to be a significant concern for you, especially in comparison to the endogenous side. And we have a good study here talking about the comparison, talking about, the different proportions that we might see in terms of oxalate coming from the diet versus oxalate coming endogenously from the amount that our bodies produce. So we'll start there. I think that'll help put this into context. So this is a study titled Contribution of Dietary Oxalate to Urinary Oxalate Excretion. And they mentioned some initial points here, which have later been found to be not necessarily correct. So we'll kind of get into the details. But the first thing they state here is that urinary oxalate is thought to be derived from three sources: 40 to 50% derived from hepatic synthesis, 40 to 50% derived from the breakdown of ascorbic acid in the body, and the remaining 10 to 20% from the diet. However, none of these estimates are based on sound quantitative techniques. So this is worth mentioning. I have seen some people who are emphasizing the endogenous side and saying that that's responsible for 90% of the oxalate exposure. And there were some earlier studies that were suggesting that, but it isn't typically quite as much. It tends to be more in like the 60% range, but it'll also vary based on how much oxalates you're getting in your diet. So we'll get into that here. They talk a bit about some of the issues with the methods that led to those percentages. And what they state is that the experimental data obtained with ascorbate more than 3 decades ago can now be questioned because of the recognition that exposure of urine or organic acids extracted from urine to the alkaline pH that occurred in these procedures results in the spontaneous breakdown of ascorbate to oxalate. So we'll come back to this later, but what they're saying is that the amount of oxalate estimated from ascorbic acid was way overestimated due to these procedures. So basically, there was not that much oxalate actually being excreted in the urine, but when they exposed the urine to the alkaline pH, then it caused the amount of ascorbate, which is coming from vitamin C in the urine, to spontaneously convert into oxalates. They then go on to say studies of the absorption of dietary oxalate and its contribution to urinary oxalate excretion have been hampered by inadequate and inaccurate data on the oxalate content of foods, by the presence of oxalate in crystalline and soluble forms in both the diet and during intestinal transit, and by limited knowledge of the processes involved in intestinal oxalate absorption. So what they're getting at here is basically there was certain context missing, some nuances missing in terms of the estimation of how much oxalate in the body was actually coming from the diet. And so they kind of set the stage with this, and then they went through, they did a study looking at the amount of oxalate that's actually coming from the diet versus what the body's producing with different oxalate levels. And we looked at this, some of this, I believe, in the last episode. What they state here is that with oxalate-containing diets, the mean contribution of dietary oxalate to urinary oxalate excretion ranged from 24% on the 10 milligram of oxalate per day diet to 41.5% on the 250 milligram oxalate per day diet, much higher than previously estimated. So again, they had a low oxalate and high oxalate diet. On the low oxalate diet, the oxalates from the diet were only contributing to about 24% of the total oxalates that the body was excreting, which is basically the amount that the combination of the amount produced and the amount coming from the diet. And then on the high oxalate diet, it was around 41.5%. They then looked at the effect of calcium here. We talked about this a bit earlier, where they state when the calcium content of a diet containing 250 milligrams of oxalate was reduced from 1,002 milligrams to 391 milligrams, urinary oxalate excretion increased by a mean of 28%, and the mean dietary contribution increased to 52.6%. So, in other words here, if you're on a low calcium, high oxalate diet, the worst combination you can basically have, the diet was responsible for about 53% of total oxalate, essentially exposure internally. And so that's worth noting. That is the absolute high end in the vast majority of cases, again, unless you're juicing tons of spinach or things like that. then you could get above that 250 milligram of oxalate level. But in the vast majority of cases, it's going to be much lower, right? Especially if you're eating enough calcium, which 1,000 milligrams is kind of just maybe barely enough. And if you're eating a more moderate oxalate diet, you'll probably be 40% or below, which would mean that the endogenous side is normally contributing to 60% or more of the total oxalates that our bodies are having to deal with. So puts into perspective here a little bit as to why we want to be focused and why it's worth going through the details here, the different pathways that can produce oxalates and how we can adjust them so that we're producing a lot less oxalate internally. And if you're dealing with oxalate issues, this is something that you really want to key in on. And as you were saying, Mike, it's so often ignored. And instead, I've seen people who think that they're dealing with these oxalate issues, and in some cases they aren't, but they're having to avoid the tiniest amount in their diet, and they're going to really great lengths to do so, when more than likely, and in many cases we see this play out, it's the endogenous side that really needs to be addressed.
Well, I think overall, at least the takeaway from me and the perspective, I think for the vast majority of people, if you just avoid the high oxalate foods and you have adequate calcium and magnesium in your diet, and then you're replete with B vitamins, then you're probably not going to have too much issues with exogenous oxalates based on the excretion going on, barring very certain circumstances we talked about with issues with the gut and things like this. Mm-hmm. So then once you have that down pat, the next question becomes, where would the next problem be with oxalates? And it's endogenous. It's going to be with the endogenous pathways. So the question is, what are all the things that can be messed up endogenously that can lead to increased production of oxalate? And the other question is, at what threshold does that oxalate actually become a problem? And that's relative to how well you can excrete it and how much is produced on a regular basis. And then also, what are other factors like the citrate or the alkalinity of blood or urine or things like this that'll change the precipitation or the ability of oxalate to actually become a problem inside the body. And so this is where I think these are the really important areas to focus on. And these are the areas that I think are less discussed overall where with these different components. I mean, you have the genetic disorders, and we'll talk about those because those will help us to highlight the important enzymes in this circumstance. That's why we're going to go through them. But fundamentally, once you have enough calcium, magnesium in your diet, and you're nutrient replete, and you're not really eating excessively high amounts of oxalates, which again, it actually would be quite a high requirement once you have adequate calcium, magnesium, because absorption drops considerably after that. Then the question is endogenous, and this is what we're going to get into in this episode: is what are we going to do what is going on endogenously, and how can we manipulate the endogenous pathways to some extent to minimize the excessive production of oxalate, and also how much of that is actually even a problem, right? Because when you're talking about percentages, you're saying 50 to 60, you're saying at the top end, absolutely top end for the oxalate stuff, you're saying 53% exogenous. But the question is, in that point, it's okay, you have 53% exogenous absorption, but what is the actual amount of oxalate that becomes a problem? And that, because these are only percentages. We're not seeing the total value. And the total value is what's important in terms of causing issues, because the body has the capacity to eliminate oxalate without it being too much of an issue.
Right. Yeah, we'll get into all those details as well. So yeah, that would be some of those really important things to consider when it comes to exogenous versus endogenous amounts of oxalate exposure. And as you can see here, coming back to this figure, the liver is going to be really central here, which also means that in general, liver function is going to be really central here, and everything that affects it, which is everything. As we often talk about, we talk about this in terms of, we went through very clearly in the fatty liver series, showing how intimately our general metabolic state is coupled to liver function. We've talked about a lot in terms of gut health and the impact of endotoxin at the liver. So there's a ton of factors there that come into play as well. And we will discuss the detailed impact of metabolic health on oxalate production in a bit. But when it comes to creating a diet to optimize metabolic function and minimize oxalate production, there's a lot of conflicting information out there. And that's why I've created the Energy Balanced Food Guide to help you determine exactly what to eat to optimally support your metabolism and help you lose weight, improve your digestion, get amazing sleep, boost your energy, and so much more. The Energy Balanced Food Guide is a one-page infographic that organizes foods on a spectrum based on how effectively they support your metabolism. And it also has a separate spectrum that adjusts the scale for you in the case that you're dealing with various digestive symptoms. The food guide makes it extremely easy to get started with a bioenergetic approach to optimizing your health. So head over to jfeldmanwellness.com/guide, where you can download your free energy balance food guide. And with that, let's talk about some of these pathways, and we'll start with the genetics here, just to get an idea of the major things that impact oxalate production. And there's 3 primary genetic defects that we'll be focusing on. It's worth noting these are extremely rare. So in the US, the percentage of the population is extremely small. It's 1 to 3 people per million that have these kinds of genetic issues. So we're talking about 0.0001 to 0.0003% of the population that would have these genetic issues. So the likelihood of that being you is, of course, very, very small. But understanding these does give us a bit of insight into the pathways here and what's really important for minimizing oxalate production and helping to kind of direct the pathways elsewhere. So Mike, do you want to start us off here with a couple of the different forms here of primary hyperoxaluria?
Sure. And I just want to put one thing into perspective as well. 80% of the genetic disorders is type 1, primary hyperoxaluria type 1, which if you have this disorder, there's a very high chance that you will have serious problems before you're even an adult, because it creates such a high amount of oxalate and stone formation at the kidney that you start to have kidney problems very early on, and then also other issues very early on. So you have a very low percentage of people are actually going to have one of these 3 genetic disorders. And in the vast majority of people, around 80%, again, we can say maybe the type 2 and type 3 may be underdiagnosed because they don't present as severely. But with type 2 and type 3 being only 20%, if you had a genetic disorder with oxalate or genetic issue with oxalates from one of these 3, you probably would know it. It wouldn't be something like, well, maybe, I don't know. It'd probably be like, pretty sure that you know that you have it going on because of how severe the presentation is. And so you have the 3 major disorders. We'll start is primary hyperoxaluria type 1, type 2, and 3. And they're basically characterized by changes in enzyme function of 3 different enzymes. So type 1 is from the enzyme alanine glyoxalate aminotransferase, which is AGXT1 or AGT. Type 2 is going to be glyoxalate reductase. And then type 3 is going to be the enzyme 4-hydroxy-2-oxalglutarate aldolase. And basically what these enzymes are doing is each enzyme is essentially breaking down or metabolizing some of the precursors to oxalate. So they're not directly metabolizing oxalate, but they're metabolizing glyoxalate, or components that lead to the production of glyoxalate, with glyoxalate being the major number 1 precursor to oxalate outside of vitamin C. And again, we already talked about this, that the contribution of vitamin C is questionable inside the body, because a lot of the methods that we're looking at with it are basically they're checking oxalate levels in the urine, and they're using methods that would spontaneously cause vitamin C to convert to oxalate. So we can't gauge on those. So outside of vitamin C, inside the body, the major precursor to oxalate is going to be glyoxalate. And these 3 enzymes adjust the metabolism of glyoxalate or the intermediaries that go to produce glyoxalate. So as an example here, the AGXT1 enzyme basically converts glyoxalate into glycine, which was shifted away from being converted into oxalate. And so in the genetic disorder, what winds up happening is you have a blockage at that enzyme, so you cannot take the glyoxalate and convert that into glycine, which means you have a lot more glyoxalate that can be converted to glycine, or can be converted to oxalate. The next one is you have glyoxalate reductase. This enzyme takes glyoxalate and converts it into glycolate. When that enzyme's function is lost, like when we see the loss of the AGXT, you get a buildup of glyoxalate because you cannot convert it to glycolate. And then that glyoxalate can then be converted to oxalate as it builds up. And then the last one is the 4-hydroxy-2-oxalglutarate aldolase, or HOG-A1. And in this enzyme, what basically happens is it's involved in the conversion of hydroxyproline into glyoxalate. And what happens is when that enzyme doesn't function appropriately, you get a buildup of intermediaries like glyoxalate that can then be turned into oxalate, or there's intermediaries that can leave the mitochondria because HOG-A1 is in the mitochondria that get converted to glyoxalate and can get converted into oxalate. Now, with that, the most significant one is primary hyperoxaluria 1 with AGXT1, because that pathway is the major pathway to get glyoxalate away from oxalate and towards glycine. The second one the glycolate reductase enzyme mutation, that one doesn't produce as severe symptoms because in the primary hyperoxaluria 2, you still have AGXT1 working, which means that you can still convert the glyoxalate into glycine. You just can't, you have a problem converting the glyoxalate into glycolate. And so the symptoms are less severe. You have less amounts or a decreased amount of oxalate production. And then the primary hyperoxaluria 3, which is even less severe than the other two, because you can still convert the glyoxalate away from oxalate into either glycolate or glycine, leads to less significant symptoms. So primary hyperoxaluria 1, you can see like kidney failure very early on because of the buildup of oxalate. Primary hyperoxaluria 2 may not really see kidney failure, but you see a very increased risk of oxalate kidney stones, and maybe down the line later in life, you start to see increased risk of kidney failure. And then primary hyperoxaluria 3, you may have some predisposition towards having issues with oxalate metabolism and may have some kidney issues, but maybe not. And so basically the 1 is the worst, 2 is the second worst, and 3 is probably the least worst of them. And again, all of these, like the oxalate kidney stones driving kidney failure from excess oxalate, is entirely derived from endogenous synthesis here. It is not derived from dietary contributions. The dietary contributions are minimal to the amount of oxalate produced in these circumstances. And so these genetic pathways are extremely helpful because what they do is they allow us to see, number one, which enzymes do we need to look at in terms of regulation of oxalate inside the body to understand like what are the bottlenecks. And that's how we're going to talk about like how are these enzymes adjusted in normal people who don't have genetic issues. And then the second thing is they give us evidence showing us that endogenous synthesis can actually be super potent in terms of causing issues with oxalates. So you have extreme examples here that you can look from and see like, hey, if metabolism of oxalate gets messed up in the body, that by itself can cause significant issues outside of what's going on exogenously.
Right. Absolutely. And that gives us a bit of a starting place when it comes to some of these precursors to oxalate and some of these pathways. And of course, as we noted, the genetic defects are extremely rare, but it does help elucidate the potential impact of these pathways, as well as notes some of the primary enzymes that are involved and are necessary to consider when we're looking at the endogenous production of oxalate. So just to kind of zoom back out here and talk about what some of these enzymes are and the precursors and kind of go through these pathways in a bit more detail. And I should mention a bit of a disclaimer. We're going to get a little technical here, but it is worth it because the more that we understand these enzymes and the different things that affect them, everything from the nutrients in the foods that we eat or supplements to what's going on metabolically, it helps give us direction as to what we need to do to minimize endogenous oxalate exposure, which obviously is extremely important. So, as you were noting, basically there's only a couple of primary pathways that actually lead to oxalate production, or a couple of primary precursors. On one hand, we have ascorbic acid, which is vitamin C, where that can directly convert to oxalates. And we'll talk about the extent to which this happens, which was overestimated in the past due to those issues in the studies and the research techniques, but now is recognized to be less, and we'll dig into that. But then aside from that, the other precursor to oxalate is glyoxalate. And glyoxalate can come from a number of different other precursors. So this is how hydroxyproline, which is an amino acid found mostly in collagenous tissue, collagen and gelatin and ground meat and other, animal protein sources. Hydroxyproline can be a precursor to glyoxalate, which can then convert to oxalate. We also have glycine, which is a potential precursor to glyoxalate, although, as we'll get to, it's a very, very minor one and not really one to be concerned with. And then there's a couple of others, but the primary other precursor to glyoxalate is glyoxal. And glyoxal is, it's a pathway in the kind of, or not a pathway, it's a component that metabolite that falls within the glycation pathways. And it's one of the very reactive, it's called a dicarbonyls. So it's a very reactive dicarbonyl within the glycation pathway. And that is also a precursor to glyoxalate. And so we'll talk about that a little bit. There's some other intermediates that we'll dig into as well. And we'll talk about the different sources for all of these. But those are kind of the primary precursors that we want to keep in mind that can potentially convert to oxalate. And so we see that here in this figure, showing these different pathways and how they can all end up leading into oxalate. And what we can see here is a couple of really noteworthy things. I mean, we see some of the primary enzymes that are involved. They note them here. And we're going to want to emphasize particular ones, right? There's certain ones that we want to make sure that we're increasing the activity of, and that's going to be the ones that move glyoxalate away from oxalate toward other possible intermediates. And then we want to minimize the activity of the ones that convert things toward glyoxalate and toward oxalate. So as you can see here, we have the AGT that we've already talked about. That's the one that's affected by primary hyperoxaluria 1. And, that converts glyoxalate to glycine. So this is one that we really want to increase, right? It's really important to have adequate activity here because glycine is great, has a ton of benefits, and it helps us move glyoxalate away from oxalate. And this enzyme is vitamin B6 dependent. So that's important to consider. And we'll talk about some other details there. So that's one thing to consider. Some of the other really important enzymes to take a look at here. One is the glyoxalase enzymes. So the reason why these are important is because glyoxal is one of the primary precursors to oxalate, and we don't want it to convert to glyoxalate because then it's much more likely to convert toward oxalate. So instead, if we can convert that glyoxal to glycolate, that helps minimize the glyoxalate production, especially because glycolate conversion to glyoxalate is generally not particularly favored. So that's normally not as much of a concern. And so the GLO1 and GLO2, those are glyoxalase enzymes, and those are going to be really important here. And these are dependent on glutathione. And so that means that oxidative stress is going to have an impact here, as we'll discuss. There are some nutrients involved like zinc, because glyoxalase, these enzymes are zinc dependent. And so that's going to be a factor. There's also some other things that use the same glyoxalase enzymes that we'll talk about that can also have some competition here. So those are two important enzymes that we want to make sure we're favoring. Another one is the enzyme, which is abbreviated GR here. That's the glyoxalate reductase, and that converts the glyoxalate toward glycolate. So again, that's another enzyme we want to be increasing the activity of. And this one is supported by NADPH that's involved in the activity of this enzyme. And NADPH, as we'll discuss, is decreased with oxidative stress and some other factors
Low
too.
carb dieting.
Yeah, we'll definitely get into that as well. The impact of low carb diets on a lot of these enzymes, because it is interesting and perhaps surprising to a lot of the crowd that's concerned about oxalates. And then we also have the HOG1, HOGA1 enzyme that converts the hydroxyproline down to glyoxalate. So we'll talk a bit about that. And then there's two important enzymes that we want to make sure that we're trying to prevent the activity of as much as possible that we'll be discussing. One of those is lactate dehydrogenase. That's the LDH abbreviated enzyme here in this figure. And that's going to convert glyoxalate to oxalate. So this is going to be a really important step here. That's normally disfavored. Normally it's a very, very small portion of glyoxalate that actually gets converted to oxalate. But if there's increased availability of lactate dehydrogenase here, that'll increase oxalate production. So that's a really important one for us to discuss. We'll talk about the different factors that affect it. And then we also have glycolate oxidase. That's the one that converts glycolate to glyoxalate. Again, that's one that's not generally favored, kind of like lactate dehydrogenase, but there also are some things that can affect it. And so we'll talk about that as well as one that we want to minimize.
What I wanted to hone in on here, just so to, I guess, simplify the overarching picture. The primary product that we are looking at is oxalate. This is the problematic component. This is the one that causes the crystals in your tissues, damages the kidneys, all this type of stuff under certain circumstances. The two most important, there's a bunch of mediators that can produce it, but I guess the two most important contributors to oxalate production in the body that we know of are vitamin C and glyoxalate. However, as we talked about, there's some concerns around how much vitamin C is actually converted into oxalate. So that leaves us with just oxalate. This is our main culprit that's getting glyoxalate. Excuse me. So glyoxalate is the main culprit that we are concerned about in terms of converting towards oxalate. So then the next question is, you think, okay, well, what creates glyoxalate in the body? And there's a couple things. There's some amino acids. The most important one is hydroxyproline. Glycine, not that important. The next thing is glyoxal. And so then from there, we're just following the money basically, right? So we have hydroxyproline and we have glyoxal are the two biggest contributors towards glyoxalate. So then what we want to do is understand what are the factors impacting glyoxalate and what are the factors impacting hydroxyproline and also impacting glyoxal. And so these enzymes that we are talking about are the enzymes that are impacting these intermediaries. And basically what we can then see is, well, what shifts the function of these enzymes? What affects these enzymes so that they have, that they lead to this increased production of glyoxalate or decreased metabolism of glyoxalate or increased production of glyoxal and conversion of glyoxal towards glyoxalate or change in metabolism of hydroxyproline and directionality of hydroxyproline towards glyoxalate. So basically, this is what we're looking at here. We just broke down, basically followed the trail. You have oxalate, the major precursor outside of vitamin C is glyoxalate, and then you have hydroxyproline and you have glyoxal as the two main precursors that are converting to the glyoxalate. And we talked about the enzymes around them that can be adjusted or affected to change the metabolism. And now what we're going to do is we're going to get into the nitty gritty on, what's impacting these enzymes and what are the states that would shift these components towards producing glyoxal and subsequently oxalate. Now, the only thing I want to mention here is that while hydroxyproline can come from the diet, it can also come from tissue breakdown. So your own collagenous turnover will increase the amount of hydroxyproline you have available, but you have the major sources, the proteins coming in from the diet, particularly collagen-rich proteins, and then you have the tissue turnover. And then for the glyoxal, the major way that we see this, Jay mentioned it, was the advanced glycation end products, AGEs, but essentially disordered metabolism. So damaged metabolism leading to the production of this reactive metabolite glyoxal that can convert to a whole bunch of things, but one of them being one of the most problematic one being glyoxalate. So we're going to get into those details now of where are we going to see these states where you have the high hydroxyproline, where are you going to see these states where you have the high glyoxal, and where are we going to see states that drive the conversion of hydroxyproline, glyoxal, and glyoxalate into those two into glyoxalate and glyoxalate into oxalate. So that's just like a 30,000 foot view of the details that Jay just laid out.
Right, exactly, and that's helpful. And there are a couple of other pathways that are worth highlighting here in a couple of these other figures from other studies, because they aren't really shown, on that other figure we were looking through, and they are potentially important here. So a couple that I want to mention. So the first one here, there's two things that are worth highlighting, especially. The first is that we see another pathway through which glyoxalate basically gets cleared away from oxalate. So instead of getting converted to oxalate, we end up seeing it head in the other direction. And in this case, it's converting into alpha hydroxy beta ketoadipate. And this is via an enzyme that's glyoxalate carboligase. And eventually this pathway goes on to produce formate. But this enzyme is TPP dependent, which is thiamine pyrophosphate.
Yeah.
Yes. And so it's TPP dependent thiamine pyrophosphate, which means that it's going to be vitamin B1 dependent. So that's going to be one area where vitamin B1 becomes important here. This is another way that we can clear out that glyoxalate. Now, another thing that's important to note here that they show is that in order to convert the glyoxalate toward glycine, we need alanine to be available. And so that's going to come into play later in a little bit when we talk about some different processes in the liver that could deplete alanine and then lead to less conversion toward glycine via AGT. That's that AGT enzyme. So just wanted to highlight that. And then we have a couple of other pathways here that are important to go into. And I didn't see them discussed really in very many papers. They seem to be kind of like lost pathways that are no longer discussed very often when it comes to glyoxalate degradation. And they're pretty important ones, and they're shown to be important in this paper and a couple others that we'll talk about, looking at thiamine depletion. And so we can see, especially we'll look at that left figure, the liver, showing the conversion from glyoxalate through two different pathways. So on one hand, we have what they call the glyoxalate oxidation cycle. So that's that cycle toward the left there. that the glyoxalate is getting converted toward into the KHG, which is 2-keto-4-hydroxyglutarate. Not that remembering the names is all that particularly important here. And so that's done via that ALD. That's an aldolase enzyme, and it's specifically 2-keto-4-hydroxyglutarate aldolase. And then it goes on to be converted into malate via alpha-ketoglutarate dehydrogenase, which, if you're familiar with the TCA cycle, the Krebs cycle, you might be familiar with that enzyme, as it's a pretty important one there. And basically, this is another part of the enzyme that is responsible for this conversion from the KHG into malate. And so that's one pathway that's also worth highlighting here. We'll talk about some different things that regulate it and help, again, to clear out that glyoxalate so it doesn't get converted into oxalate. And then there's another pathway that they talk about via the alpha-ketoglutarate carboligase. And here they show that that the glyoxalate via this pathway gets converted to HKV and HG, which is 5-hydroxy-4-ketovalerate and 2-hydroxyglutarate. Again, the specific names not being as important here, but there are some important things that affect these pathways. So we'll come back to them later. And just while we're going through all the details of all the different things that could lead to oxalate production and can help to clear out the metabolites that lead to oxalate production, it's worth highlighting these couple. And then there is one other figure that we'll go through here showing the primary glyoxal sources. And considering that that's the primary contributor to glyoxalate, that's a very important place to focus. But before we do that, Mike, is there anything you wanted to mention?
I just wanted to put this picture in context that you're discussing, is that if you have problems in the Krebs cycle, or if you have a thiamine deficiency, is basically what you're discussing here, you will not be able to metabolize glyoxalate appropriately, so that they'll lead to a buildup of glyoxalate, which can then lead to a buildup of, or an increased production of oxalate. So basically, you're just showing multiple mechanisms by which, basically, if you have like an issue with alanine, like you don't have enough alanine, or you don't have enough thiamine, you won't be able to actually get rid of or metabolize glyoxalate away to other products. So then that it can be converted, you'll leave more glyoxalate, which can be converted to oxalate. And then the picture here is showing that you just went through is specific for the Krebs cycle, or basically the major cycle in the body responsible for energy metabolism, as well as an enzyme there that's thiamine dependent, another thiamine dependent enzyme. So nutrient deficiencies and also the damaged metabolism can further change the amount of glyoxalate that you have, which again is a major precursor to oxalate. And so if you build that up, you can start to increase conversion towards oxalate. And that's why you're going through these.
Right, exactly. And just to clarify, in this last figure, the conversion via the carboligase enzyme that they're describing, that one is thiamine dependent. And then the one through the glyoxalate oxidation cycle, the aldolase enzyme, and then the alpha-ketoglutarate dehydrogenase, those aren't actually affected by thiamine. But as you were saying, alpha-ketoglutarate dehydrogenase can be interfered with if there's interference in the Krebs cycle, and specifically low NAD to NADH ratio will impact that. And then they also mentioned in the study, and you can kind of see it, that there's a kind of squiggly arrow next to the aldolase and the alpha-ketoglutarate dehydrogenase, representing that they're actually inhibited by the presence of glyoxalate. So if you have glyoxalate buildup, it actually, in this case, decreases these particular pathways that helps to clear it, which is an interesting kind of feedback cycle that you don't see very often, but worth highlighting here. That brings us to the last of these. Again, more complicated pathways. I know we're going through the details here, but it really is worth at least kind of getting semi-familiar with, because it'll make a huge difference when we talk about what we want to do in terms of minimizing our production of oxalates. Now, in this last figure, it's a pretty complex one, of course, and we're not going to be focusing in any sort of detailed sense here. But what we're looking at here or what we're trying to focus on here is the actual production of glyoxal, since glyoxal is going to be that really central precursor to glyoxalate. And so they note a ton of different possible things that can lead to glyoxal production. One of the most important to highlight, and really the primary one, is lipid peroxidation. And we've talked about this a lot. We'll continue to talk about it. But lipid peroxidation is something that we see when we're consuming high amounts of PUFA. And when, as a result of that, the structure of the cells is made up of a lot of PUFA, a lot of the unsaturated fats that are very unstable and they're very susceptible to becoming peroxidized. It's also something that happens if we're producing a lot of oxidative stress, or if we're in an inflammatory state, if metabolically we're struggling, because all of those things will increase reactive oxygen species production. And if you have that alongside PUFA, especially That's a recipe for a lot of lipid peroxidation. There are some other precursors to glyoxal that come from carbohydrates. In general, the ones that are coming directly from the glucose itself are pretty slow forming. They're pretty rare because glucose doesn't typically just stay as glucose. We're metabolizing it pretty quickly ideally into energy. If not, we're storing it as glycogen. And there's not much just kind of sitting around to spontaneously become glyoxal. It can interact with proteins and create some glycation products. But again, this is something that takes a long time. And unless we're dealing with chronically very elevated glucose due to impaired glucose metabolism, which we've talked about extensively, and I'll link back to some of those episodes as to what causes that, and it's not carbohydrate consumption, that can also cause some glyoxal formation and also certain intermediates in glucose metabolism. If there's buildup of these, if we're not effectively converting that glucose all the way through producing lots of ATP, all the way through glycolysis and then through the Krebs cycle and through the electron transport chain, you can have buildup of these intermediates that can contribute to glyoxal formation. But really, more than anything, it's the lipid peroxidation that is the primary driver here of glyoxal. And we want to be very much aware of that, since glyoxal is going to be the primary contributor to glyoxalate, which is the primary contributor to endogenous oxalate production.
I just want to add here, for the picture, is that the problem with the glucose oxidation, and especially if you start going through the studies, is that the oxidation is impaired. So you have issues at the mitochondria, which leads to a backlog, which that backlog of the metabolites, basically all the way from the mitochondria in through glycolysis, is what leads to the backlog of the metabolites in glycolysis, the conversion of glucose to pyruvate. That backlog there is what drives some of the glycation or the production of glyoxal of these reactive components. So the problem isn't the carbohydrate by itself. The problem is an inability to effectively oxidize or use the carbohydrate as a fuel source, which leads to a backup of metabolites that leads to deranged metabolism, and then you get an increased production of glyoxal. And this I think is really important, because a lot of people talk about carbohydrate being a major driver for reactive components like glycating components like glyoxal and things like this. But the problem when you start going through the studies is actually the disordered metabolism. So I really want to highlight that it goes down to disordered metabolism, because this is also something that we're going to come back to. That's going to be, I think, exceptionally important to discuss as a primary driver for the increased production of glyoxal and also oxalate. So you're just seeing glyoxal, 2-glyoxalate, 2-oxalate. So you're seeing again, like how important optimizing metabolism is in terms of optimizing multiple metabolic functions, whether you're looking at this from a diabetes or blood glucose dysregulation standpoint, but also from an oxalate production standpoint. If metabolism starts to go awry, you get back up in all these products, and some of them can be potentially problematic and create a variety of issues. But the issue is not the fuel. The issue is the utilization of the fuel, which is like the primary thing that we are, beating the dead horse with on this podcast.
Yeah, well, you have to do it, because otherwise, it's just constant influx of people saying that it's the carbohydrates causing it. So.
Yeah. Yep. And another thing too is the lipid peroxidation that's occurring is from disordered metabolism as well. So if you have disordered metabolism and you have inflammatory signaling, you have oxidative stress, that's going to increase the amount of lipid peroxidation. And also, if a lot of your lipids, if your tissues are stored up with polyunsaturated fatty acids, then you're sitting on a nice pile of dynamite and you're just waiting for those fuses to light. When you light those fuses, you get a variety of lipid peroxidation products, which on top of this ordered glucose metabolism can drive this glyoxal production, which is basically what you're showing. And this is just one way that it's problematic, is driving the glyoxal production, not to mention the lack of conversion of glucose to ATP, as well as the increased lipid peroxidation being problems in and of themselves outside of glyoxal. We're just highlighting it for oxalate metabolism here, but they are also problems by themselves, which we've covered in previous episodes.
Yeah. And not to mention that glyoxal itself is problematic. Even if it doesn't get converted to oxalates, it's a pretty reactive dicarbonyl. And so it can damage DNA and proteins and all sorts of things and lead to age production, advanced glycation end product production. So yeah, that in and of itself is also problematic. And then again, you mentioned the influence of oxidative stress here. And if you're unsure as to which fuel, whether it's carbs or fats, that leads to more reactive oxygen species per ATP produced, you might be surprised. Again, I would take a look at those studies that we link to here, where we've talked about all of that in detail.
And it's fats.
Right.
You didn't tell him. You just left him hanging on the cliff.
It was supposed to be a cliffhanger, but all right. But they got the sneak peek. All right. So let's talk a little bit about that contribution from each of the primary sources. We have alluded to this, that glyoxalate is the main precursor to oxalate, but there's a lot of discussion about this and people suggesting different things. So it is worth talking through some of the discrepancies here and where they come from. We alluded to one of them earlier, which was the kind of older studies that weren't looking at ascorbic acid properly and other things. So we'll dig into all of that here. Again, we're going to come back to this study, the one titled Contribution of Dietary Oxalate and Oxalate Precursors to Urinary Oxalate Excretion, where they state the role of glycine in oxalate synthesis was initially thought to be a major one, with contribution to oxalate synthesis estimated as high as 40% in older studies. However, a study of 6 healthy volunteers using improved analytical method, including dietary control and primed constant infusions of, it looks like, radioactively labeled glycine, demonstrated that glycine metabolism contributed less than 5% to urinary oxalate. So again, something that is often discussed, was vitamin C being a contributor, but also glycine. And what they're pointing out here is that was way overestimated in the past in terms of glycine. And rather, glycine is a very, very small contributor to urinary oxalate. And again, they explain that here with ascorbic acid with vitamin C, where they state studies by Atkins et al. And Baker et al. Indicate that ascorbic acid may be the largest contributor to endogenous oxalate synthesis, contributing approximately 40% to urinary oxalate excretion, which, keep in mind, if we're thinking 60% of the urine oxalate excretion is coming from endogenous synthesis, and 40% is from ascorbic acid from vitamin C, that would mean that 2/3 of the endogenous synthesis is coming from ascorbic acid. But they then go on to state that the methods used at that time had limitations, and thus studies readdressing the role of ascorbic acid in endogenous oxalate synthesis are needed. So we'll continue to talk through this, but vitamin C is not at all a major contributor like it used to be thought, or at least as major of a contributor to endogenous oxalate synthesis.
Yep. Yeah, the reason that they found that out is because basically the way they were testing oxalate levels in the urine, what the reagents, the products that they were using to test the urine were basically forcing vitamin C to convert to oxalate. And so when they took out the urine and tested, they're like, oh, wow, look, there's all this, we gave people the vitamin C, and then they look at all this oxalate it produced, and the researchers saying, well, actually it was an artifact of the testing methods. So it's not as much as previously estimated. That's the general point.
And actually, just to clarify, it looks like the 13C labeling for the glycine, it's not actually radioactive labeling. I misstated that. But let's talk a little bit about, or continue to go through these studies, looking at different contributions to oxalate production. Mike, why don't you go ahead and share this one, discussing hydroxyproline.
So they have a paper here titled Hydroxyproline Metabolism and Oxalate Synthesis and Primary Hyperoxaluria. And they say here, observed that hydroxyproline metabolism contributes 15% of the oxalate excreted in urine of normal individuals. Prior studies with C-glycine infusion suggest that glycine metabolism contributes up to 5%. Dietary oxalate accounts for 40% of total urinary oxalate excretion, with the remaining 60% derived from endogenous oxalate synthesis. Thus, in healthy subjects, hydroxyproline and glycine combine for approximately 1/3 of endogenous oxalate synthesis. What we're showing here is that vitamin C is overblown as a precursor to oxalate. And so the major precursor to oxalate is glyoxalate. And with that, hydroxyproline and glycine account for 30% of that endogenous synthesis. And then essentially, the vast majority of that is coming from hydroxyproline. So what we just established is we're not as worried about vitamin C contributing to oxalate. We're mostly worried about glyoxalate and for endogenous synthesis, and of the glyoxalate, the conversion to glyoxalate, hydroxyproline is the main amino acid that is being converted to the glyoxalate. Glycine isn't really the main amino acid. So the next question is, what is the next major precursor to glyoxalate, which Jay is going to explain for us here.
Right. And it's worth noting as well that they mentioned that the glycine contributes up to 5%. So they're kind of overestimating at the high end there, when really, it could be considerably less, but it is suggesting that some portion is coming from hydroxyproline. So that is one to consider. And we'll kind of keep going through here. There's two things that are important to note here. So one, In this first study that's titled Hepatic Alanine Glyoxalate Aminotransferase Activity and Oxalate Metabolism in Vitamin B6 Deficient Rats, they note that approximately 50 to 60% of urinary oxalate is derived from the endogenous metabolism of glyoxalate. So this is speaking to that point that you had mentioned, Mike, which is that if we know out of all of the urinary oxalate, about 60% is endogenous, and they're noting that almost all of that is coming from glyoxalate, that means that vitamin C, ascorbic acid, which does not go through glyoxalate, it just converts directly to oxalate after a few steps, is not a major contributor here. So that's the important point here. They also mention, of course, that glyoxalate is converted to glycine via AGT in the liver, and vitamin B6 has an important role as a coenzyme. But then in this next study, they talk about the primary source of that glyoxalate. That's, our real question here, considering that that's the major driver of the endogenous oxalate synthesis. And so this is a study titled Glyoxal Formation and its Role in Endogenous Oxalate Synthesis. And they state it's clear that glyoxalate is the major precursor of oxalate. The metabolism of a number of substances has been proposed as a source of glyoxalate, including glycine, phenylalanine, tryptophan, hydroxyproline, glucose, fructose, pentose sugars, ethanolamine, and glycolate. Our research to date indicates that of these potential sources, hydroxyproline makes a modest contribution of 5 to 10%, and the majority of others provide negligible amounts. So I'll just pause here. First off, they're noting an even smaller proportion coming from hydroxyproline. So it's still the largest one other than the primary one they're going to mention, but really not that much. They also note, glucose and fructose here. We'll come back to those later. They do mention that the others provide really negligible amounts, but it's always worth mentioning when, glucose and fructose are to blame kind of for everything. But they go on to say, we have found, however, by incubating a variety of 2-carbon molecules with hepatocytes, that glyoxal is a prominent source of glyoxalate. We hypothesize that glyoxal is one of the most important sources of endogenous oxalate synthesis in humans and possibly other organisms, and is one that has been overlooked to date. Mounting evidence is also suggesting that both glyoxal production and oxalate synthesis can be associated with oxidative stress, which we'll be digging into here in a moment. But again, really highlighting that primary focus that we want to be looking at is glyoxalate. How do we convert it away from the oxalate? And what are the things that are primarily converting toward it, with the major one being glyoxal? How can we try to prevent that? How to convert that glyoxal toward glycolate via glyoxalase, as we discussed, the impact of oxidative stress and all of that. So obviously a little bit technical here, but really worth highlighting, because when you just look at a pathway, and I don't want to get too far down this tangent, but when you just look at a pathway and you see, glycine could be, it has one way of converting into glyoxalate, so that must be a major precursor to oxalate. People will do that with all sorts of things, with hormones, all sorts of different pathways, and it's worth noting
pregnenolone steel, Jay.
Exactly. Yeah, and with vitamin D, there's so many different things. Obviously, with vitamin A as well, and there are so many details to consider, like in what compartment of the cell is this happening? And does that enzyme largely exist in that cell? Or what other enzymes are competing with it? What are the cofactors? What are all the things that lead to the regulation that could cause one precursor to be way more of a precursor than another? What's its availability in different compartments? All of that. So that's why it's so important to really highlight these things for people who feel, who might not recognize why we need to understand all of that. But it is really important. And then it can allow us to focus on these primary things, like how do we reduce glyoxal production? How do we minimize the conversion of glyoxal to glyoxalate, which will then help us lower the amount of oxalates our body is producing.
Yeah, we basically need to know who the primary culprits are. We need to know who's caught red-handed in this metabolic crime. And basically the two that we've gone to is hydroxyproline and glyoxal being converted into glyoxalate, and the glyoxalate converting to oxalate. And so basically the point of all these studies is to lay all this out so that now we could talk about what do you actually do about this? How do you solve this? And so that it kind of eliminates the other things that you hear from different places. Well, it's glycine or it's vitamin C. It's like, no, if we really want to hone in after we go through the research, we really want to distill this down. It's like, okay, maybe there's some from vitamin C, but the amounts potentially overblown. The major is really glyoxalate. And then what is creating glyoxalate? Hydroxyproline and glyoxal. And so we've narrowed down to some of the two major culprits. And now we can say, well, how are they committing the crime? And that's the next question. That's what we're going to jump into.
Right. Exactly. And as we've discussed, oxidative stress it was mentioned in that last study and is something that impacts a number of the different enzymes that affect glyoxalate metabolism. And so that's a really important one to key in on here. We'll talk about a number of things that contribute to excess oxalate production or reduce the amount of oxalate production. And oxidative stress is a huge one. Again, we've talked in detail about what are all of the things that affect oxidative stress. And we're going to talk here about some of the kind of more surface level things, which are worth noting. But this, for example, we'll talk about glutathione. This doesn't just mean you need to take glutathione or focus on the things that increase glutathione. Instead, we need to zoom out, consider the larger metabolic state and what would cause the depletion of glutathione in the first place, what's causing oxidative stress and inflammation that's driving the need for this. So I do want to be careful, as far as takeaways here, that we don't get too caught up in the idea that this is some isolated thing that we need to be increasing on its own, as opposed to considering the larger picture. And so there are a couple of studies that we're sharing here talking about the impact of oxidative stress and how it impacts some of these enzymes. So the first one is titled Contribution of Dietary Oxalate and Oxalate Precursors to Urinary Oxalate Excretion, a study that we've referenced a few times here. And they state, in a study utilizing human erythrocytes, glyoxal was shown to be preferably converted to glycolate, with 1% ultimately converted to oxalate via glyoxalate. So just to pause there, it's worth noting that in a lot of these different pathways, the actual conversion to oxalate is typically disfavored, right? We talked about this where in general, glyoxalate likes to be converted toward glycine in the vast majority of cases. That's one situation here. But in this case, they're talking about the glyoxal itself, where glyoxal isn't actually, even though it's the primary precursor to glyoxalate, in general, it doesn't want to be converted to glyoxalate. It actually wants to be converted to glycolate, which is much better because glycolate also doesn't really want to be converted to glyoxalate. However, they go on to state the formation of oxalate was increased when intracellular glutathione was depleted, highlighting a potential role of oxidative stress in endogenous oxalate synthesis through this pathway. So what they're saying is that when there's oxidative stress that depletes glutathione, it increases the amount of glyoxal that gets converted to glyoxalate instead of glycolate. And part of that, or primary reason there, is because the enzymes that convert glyoxal to glycolate, which is the glyoxalase enzymes, are glutathione dependent. So if there's oxidative stress and you have a lack of glutathione, we can't convert the glyoxal to glycolate as effectively, and instead more of it will be converted to glyoxalate. So that's the main, one primary concern here when it comes to oxidative stress impacting these pathways. Mike, do you want to go ahead and share this next study?
So following up to that, adding some perspective to show that if you correct oxidative stress, you can actually minimize the conversion of the glyoxal towards glyoxalate. We have a paper titled Hyperoxaluria, the role of N-acetylcysteine and vitamin E on the lithogenic factors and urinary markers in ameliorating calcium oxalate crystallization. The authors say, N-acetylcysteine and vitamin E pre-treated animals showed a significant decrease in stone-forming risk factors in urine and increased inhibitor excretion. Histologic sections showed NAC and vitamin E pre-treated hyperoxaluric rats inhibited deposition of calcium oxalate crystals and renal cell damage. So basically, if you have rats that have hyperoxaluria, so they have a high amount of oxalate floating around, that typically would wreck their kidneys and cause stone formation in their kidneys. If you give them N-acetylcysteine, which is a direct precursor to glutathione, and you give them vitamin E, which helps to regenerate glutathione, what you see is that there's less stone formation. And why would there be less stone formation? Because there's less formation of oxalate. And you also see the less damage to the actual, the kidneys, which are the main site that gets damaged from oxalates in general. And they further say, N-acetylcysteine therapy prevents calcium oxalate retention by protecting against membrane injury, thus maintaining a smooth urothelium that does not favor stone formation. So the other thing that they showed here is that outside of production, outside of just the having antioxidant enzymes or antioxidant substances that help to maintain glutathione status, which decreases oxalate production, if the tissues have adequate oxidative antioxidant protection, then you're less likely to get damage from the oxalates by themselves because they create oxidative stress, which we talked about in the previous video. They can actually drive lipid peroxidation themselves. And then therefore, when you don't get the membrane damage, the stones are unable to adhere to the damaged areas, or the calcium the calcium oxalate crystals don't deposit in that area and eventually form a larger stone they're just excreted out because the lining of the inner portion of the kidney is actually able to keep itself smooth so that you don't get the aggregation or the buildup of these crystals. So basically, like the way you can think about it is if you have a pipe and the pipe has the pipe is very smooth inside. If you have products running through the pipe, no problem. Like they'll just run through, they'll slip off the sides, they won't stick. But if you start getting damage to that lining of the pipe, maybe you get an area where you can start to get product building up, some gunk or junk inside the fluid flowing through the pipe will stick to the sides. And so basically what you're showing here is that if the body has adequate antioxidant status, it can actually protect its pipes, particularly in the kidneys, from the damaging effect of the stones. And you'll probably get less stone formation because you have adequate glutathione status, which will shift the glyoxal away from glyoxalate, which can get converted to oxalate, and towards glycolate.
Right, exactly. So a couple of different really important areas through which oxidative stress impacts, the oxalate situation, right? Oxalate production and also the damage that can be produced from oxalates, whether they're coming from our diet or endogenously. And obviously, oxidative stress is something that is associated with an impaired metabolic state, something that, in general is the primary focus, whether we're talking about that being driven by endotoxin or PUFA or poor glucose metabolism. And we see this play out in states characterized by those things. When we look at diabetes and obesity, cardiovascular disease, non-alcoholic fatty liver disease, we see issues with these pathways, and we see increased oxalate excretion and different interaction with these enzymes. So we're seeing it play out in people who are dealing with these things. We're actually seeing the impacts. And so we'll take a look first at people with type 2 diabetes, looking at the fact that they have increased oxalate excretion and also increased levels of glyoxal and glyoxalate. And in addition to that, they also have increased levels of methylglyoxal, which we'll get to in a moment. So this study is titled Glyoxal and Methylglyoxal Levels in Diabetic Patients, Quantitative Determination by a New GCMS Method. And so we can see in table 3 here that there are 2 different groups, A and B, and then there's the control group. So groups A and B are different patients with diabetes. Group B they underwent some sort of intervention to improve their glycemic control. And then group C is the just regular people who don't have diabetes. And so you can take a look at the glyoxal levels between group 1 and the kind of uncontrolled diabetes or without the interventions to improve it, and the control group, and they have more than 2 times the amount of glyoxal levels in the people with type 2 diabetes. And they also have significantly more methylglyoxal as well, as much as 3 times. Now, the reason why the methylglyoxal is important here, and we can see this when we look back at that figure showing the production of glyoxal, is that we see that methylglyoxal also uses the glyoxalase enzyme in order to be converted to D-lactate to help basically detoxify the methylglyoxal. And so if the methylglyoxal is also using up the glyoxalase, that means there's less glyoxalase available for the glyoxal to be converted into glycolate, and more of it will be converted into glyoxalate. So there's a handful of different issues here that can be leading to the fact that, or contributing to the increased oxalate excretion that we see, meaning increased oxalate levels in people who have diabetes. And it's not just because all of them are eating spinach salads. I would assume that most of them are not doing that, but rather it's because of the endogenous oxalates that they're producing, which would include, largely being driven by the glyoxal levels that they are producing in increased amounts due to increased lipid peroxidation, due to impaired glucose metabolism. And so, very important highlight in terms of the impact of endogenous oxalate production, and also the impact of oxidative stress, inflammation, and glucose metabolism issues on oxalate levels. And we do see this with obesity as well. So not just type 2 diabetes, but also in obesity, we do see elevated levels of oxalates and glyoxal and all of that.
Yeah, and it's not just it. You mentioned lipid peroxidation, and you also mentioned impaired glucose metabolism. But it's also directly through the oxidative stress, depleting glutathione, which would shift the glyoxal towards glyoxalate in these states. So what you're showing here, Jay, is that in this diabetic state, you have a higher amount of glyoxal, probably through the metabolic aberration by itself. But the metabolic aberrations themselves are going to drop glutathione, which is then going to further shift that glyoxal towards glyoxalate, and that glyoxalate towards oxalate. And then on top of that is, even if glyoxal even if you wanted glyoxal to be shifted towards glycolate, or if you wanted it through the glyoxalase enzymes, number one, you don't have the glutathione, as I mentioned, but number two, now it's got to compete with methyl-glyoxal at the glyoxalase enzyme. So it's like multiple factors just pushing this pathway towards like a glyoxalate and then towards oxalate. And then on top of this, and we'll get to this in just a second, but if you, in the diabetic states or the metabolically impaired states, you have excess gluconeogenesis going on, which is probably going to deplete certain amino acids like alanine, which you actually need to convert your glyoxalate to glycine. So it's just basically like you're like lining up a pathway to create glyoxal and then shift it towards oxalate production. And this is not related, as you said, to dietary factors. This is related to the metabolic state and the context with which people find themselves in. And in the research, there's associations with diabetes and with obesity and metabolic dysfunction in driving the production or an increased risk of kidney stones, particularly oxalate kidney stones. And so now we're basically outlining some of the potential pathways on why this could happen. And it's based on the state. So again, this is like showing how the state changes in metabolism can increase the production of oxalate, which can basically, you're seeing that through these mechanisms as well as the increased risk of oxalate kidney stones in these populations.
Right, absolutely. And as you alluded to, there's a couple of mechanisms as well relating to gluconeogenesis and the state of diabetes, elevated glucagon, that will all come into play here. But yeah, a lot of things all driving this toward the dysfunctional state, just like in every other chronic health condition that we see. The metabolic dysfunction is really at the root and drives everything in a negative direction. And whether we're talking about liver fat accumulation, whether we're talking about degenerative states in the brain, whether we're talking about oxalates, whether we're talking about atherosclerosis, it all comes down to these fundamental baseline things. And that's something else that we want to come to throughout this episode, digging through all the complexities here, is coming back to the basics, right? Obviously, sometimes it requires the explanation of some of the complex things to elucidate the fact that it really does come back down to the foundations and the idea that we want to be focusing on oxalates as the boogeyman and everything needs to be focused on oxalates. Rather, it's just, in most cases, an effect of the general degenerated state. And that's why you see it in type 2 diabetes and obesity. You also see it in cardiovascular disease, as well as non-alcoholic fatty liver disease, both of which are also great examples of just baseline metabolic dysfunction causing chronic health issues. Mike, do you want to go ahead and share this one, specifically focus on atherosclerosis and also touching a bit on fatty liver?
Sure. So we have a paper here titled "Dysregulated Oxalate Metabolism is a Driver and Therapeutic Target in Atherosclerosis." So they say is impaired biosynthesis of glycine in atherosclerosis was suggested by evidence of a decreased glycine and serine ratio in plasma from patients with unstable atherosclerotic plaques. Furthermore, transcriptomics of human and mouse livers revealed suppressions of genes driving glycine biosynthesis from serine, alanine, and glyoxalate in non-alcoholic fatty liver disease, predominantly through the enzyme alanine glyoxalate aminotransferase. So basically what you're seeing is when they look at people who have atherosclerosis, what you see is that they have lower levels of glycine in their blood, in their serum. And then also they have lower levels of glycine in ratio to serine. It's another way to gauge where the glycine, the amount of glycine is present. And they're saying that the reason that these people have lower amounts of glycine is not necessarily because they're taking in less glycine. I mean, that could definitely be a possibility as well. But at the same time, what they're saying is that the enzyme AGXT1, alanine glyoxalate aminotransferase, that we talked about with primary hyperoxaluria 1, is actually downregulated in states like non-alcoholic fatty liver disease, which would be associated strongly with different metabolic diseases, including atherosclerosis. And what you're seeing is that the conversion of glyoxalate, to glycine through that enzyme actually becomes impaired. So that by itself will drive a decreased amount of glycine inside the blood. So you're seeing the lack of glycine in these metabolic states. These impaired metabolic states could actually be driven by a downregulation of this enzyme that is converting the AGXT1, that's converting glyoxalate into glycine. And so the metabolic aberration is driving the production of the maintenance of glyoxalate, which can then convert into oxalate. And so this paper is actually is discussing the dysregulated oxalate metabolism inside atherosclerosis. And this is actually important as well, because we know that oxalate itself can damage the vasculature. So it's like another factor where you can have this metabolite oxalate if you have, issues going on with the liver, issues going on with glucose metabolism, issues with accumulating large amounts of body fat in the obese state, which would arguably be triggered by issues with metabolism at the cellular level. You can also increase toxic components like oxalate, which can further worsen and or drive atherosclerotic plaques or processes, because the oxalate can damage the vasculature, and the metabolic state is what's driving it. It's not the spinach salads. It's not the kale juice or the collard green juice or whatever the thing is. I mean, we're not saying that that's not a problem. What we're saying is in these states, the metabolism could drive it. And this is, again, just bring this into context. The endogenous synthesis is not something that's massively discussed, but it's also important to see here that it could be a key factor, and it may be involved in multiple disease states beyond just people who are having issues with oxalates.
Right. Absolutely. And in this study, they also talk about seeing a decreased glycine to oxalate ratio in patients with atherosclerosis. And again, highlighting that this is impairing the functionality at the liver to, and within that, it's affecting the AGXT enzyme, the AGT enzyme that's converting the glyoxalate to glycine. So, and they talk as well about the actual negative effect of the lack of glycine availability, which of course is a major issue when it comes to atherosclerosis. We want to have enough glycine available, which is very, very protective. And we have this other study looking at this in more detail in non-alcoholic fatty liver disease. And it's worth noting, especially because it speaks a little bit to how little glycine actually converts to oxalate, because we know that that's, even in cardiovascular disease and NAFLD, where one of the primary issues is that we're getting conversion toward oxalate instead of glycine. So we have an underlying metabolic issue. But what they show here is that if you provide glycine, it still provides benefits despite all those issues, and it's still not a major contributor to oxalate production. And so this study is titled "Glycine-Based Treatment Ameliorates NAFLD by Modulating Fatty Acid Oxidation, Glutathione Synthesis, and the Gut Microbiome." And they state lower circulating glycine is consistently reported in patients with non-alcoholic fatty liver disease. We performed transcriptomics in livers from humans and mice with NAFLD and found suppression of glycine biosynthetic genes, primarily AGXT1. Glycine-based treatment attenuates experimental NAFLD by stimulating hepatic fatty acid oxidation and glutathione synthesis, thus warranting clinical evaluation. And so in this study, basically, they saw these issues metabolically going on at the liver, in this case, looking at non-alcoholic fatty liver disease. But despite that, providing glycine was still net beneficial and helped to prevent the non-alcoholic fatty liver disease. So pretty telling, and again, highlights the fact that we really don't want to be concerned about glycine consumption when it comes to oxalate production, even if we have these underlying metabolic issues.
And this is actually something I use with clients quite a bit who are dealing with metabolic dysfunction or fatty liver. Is I use glycine in combination with protein like whey protein, which is rich in cysteine, or you could do collagen and whey protein, depending, but you'd get higher hydroxyproline, particularly for an oxalate issue. So you could use glycine plus a whey protein, and that can increase the amount of glutathione that you're producing. And also the whey and the glycine together can help to improve the liver function overall by providing other amino acids that are important for metabolic processes, improving the glutathione synthesis, and helping to decrease the amount of fat present in the liver. So I would say, it's important that we actually show that glycine isn't a problem for the oxalate issues, especially in people who have impaired metabolism that's driving the oxalate issues, because the glycine can actually be a useful treatment for these people. Plus, the glycine can help with bile acid synthesis inside the intestine, which will allow you to actually absorb your fats so that they don't complex with calcium, so that the calcium in your intestine can bind with the oxalate and then decrease dietary absorption. So I would say that glycine, on the whole, like if we were to take all the mechanisms of glycine compared to this like less than 5% conversion into the glyoxalate, I would say that glycine is probably a net benefit for people dealing with oxalate issues and likely not a primary driver. More of the concern would be maybe hydroxyproline and also metabolic dysfunction, glyoxal, and then the dietary stuff beyond glycine. So I'd say this is just further evidence on top of what we've discussed before, where glycine is not really the culprit here. So basically, like, glycine can go free, but hydroxyproline and glyoxal, like, they're still on the hook. Like, they still have to be detained.
Sure. And proportionally much more the glyoxal concerns rather than hydroxyproline. But yes, as you're saying, especially if there's underlying metabolic issues and someone's dealing with oxalate issues, then hydroxyproline should be looked at maybe a little bit more closely. But again, a net benefit by far when discussing glycine provision, especially as you said, considering the improved bile flow, improved fatty acid digestion, which then reduces oxalate absorption, which we talked about in that last episode in part 1 of this series. So this brings us to the impact of gluconeogenesis and glucagon. So this is important for a number of reasons. For one, the chronically high levels of stress hormones increase gluconeogenesis at the liver. It increases glucose production from other substrates to provide that fuel so that we can deal with whatever stress is going on. We've discussed this in detail, link back to those episodes. So anything that chronically elevates stress hormones will increase gluconeogenesis, which will have an impact here on oxalate production. Now, there are certain things that will do this far more than others. And in general, we're not concerned about, a short-term burst of some of these stress hormones, like if you're exercising or something like that, or, a little bit of an increase in the stress hormones in the morning to, as you wake up, the dawn phenomenon, all of that. That's not really concerning, but we're more concerned about chronically elevated stress hormones. And there's one situation we've talked about that this is really primarily implicated is insulin resistance and impaired glucose metabolism, type 2 diabetes, where hyperglucogonemia is a primary driver there. And also you tend to see high levels of cortisol and adrenaline as well. I'll link back to those episodes. Another one is a low-carb diet, which we'll be focusing on in a bit more detail in the next part of this series. But you got to get a little taste here, where if you're not getting carbohydrates from your diet, you're going to be producing them endogenously. And despite the fact that we're told that there's no cost to that and you should just let your body determine how much glucose it wants, there is a major cost to that. We've talked about that prior in terms of an energetic cost, in terms of urea and ammonia production, things like that, especially ammonia, really, not so much the urea.
Glucocorticoids.
And yeah, the hormones required to drive that state, of course, which is coming from the lack of energy from the lack of glucose in the first place. So pretty rough state. But interestingly, it also comes into play here when it comes to oxalates. Mike, do you want to go ahead and share the study?
Sure. So the study is titled "The Effect of Dietary Protein and Glucagon on the Urinary Excretion of Oxalate in the Guinea Pig." Glucagon treatment, the authors say here, glucagon treatment increased mean urinary oxalate excretion by 77% in male and 34% in female animals. Glucagon decreased hepatic alanine levels by 66%, lactate by 69%, and pyruvate by 73%, but glycolate and glyoxalate levels were unaffected. This decrease in alanine would substantially lower the activity of the AGXT enzyme activity in vivo and make more glyoxalate available for oxalate synthesis. The decrease in lactate and pyruvate concentrations would stimulate the enzymatic conversions of glyoxalate to oxalate and may account for the increase in oxalate synthesis without an increase in glyoxalate concentration. So basically what they're saying is, a couple things to set the stage here, which we kind of already did, but just to get back a little bit to put the context, we have the enzyme AGXT1 that takes glyoxalate and it converts it into glycine. So it's basically getting rid of glyoxalate for us. Now, it's dependent upon these components here, specifically alanine and also specifically pyruvate. So if you don't have enough alanine and pyruvate because you're heavily driving gluconeogenesis, then what winds up happening is you are actually forced to, the enzyme is forced to not actually take the glyoxalate and convert it to glycine. So it leaves the glyoxalate present because it doesn't have the pyruvate and it doesn't have the alanine to get rid of that glyoxalate. But then the next thing that happens is the major enzyme that converts glyoxalate into oxalate is lactate dehydrogenase. And the lactate dehydrogenase, now that it doesn't have the pyruvate present to take the pyruvate and convert that pyruvate to lactate, what winds up happening is you now have this enzyme. It's like the doors are open for business and it's going to take this glyoxalate and it's going to convert that glyoxalate into oxalate. So you're setting up a circumstance by driving excessive gluconeogenesis where you're actually going to allow for more glyoxalate to be present and more of that glyoxalate to be converted into oxalate. And so again, the states where we see this, we have entire episodes talking about how glucagon is high in people who are glucose impaired, people who are diabetic, people who are obese. And then on top of that, the low carbohydrate dieting, keto dieting, carnivore dieting especially also drive increased glucagon production, which can worsen worsen or increase the production of oxalate through these very specific mechanisms. So this is another example where changes in metabolism can shift the products that are produced. And in this circumstance, what we're seeing is just going on a low carbohydrate diet or having a low carbohydrate, high protein diet is even worse, which would be a carnivore diet. You basically can increase the production of oxalate by shifting metabolism at the liver. And this just, I guess, is another hint, spoiler alert, is probably one of the things that is driving oxalate dumping on these different diets. It's one of the mechanisms, and there's other ones involved with this, but this I think would be a key one.
Yeah, absolutely. And again, just to kind of clarify what's going on by looking at this, the figure that we have looking at these pathways, we see a reduced conversion of glyoxalate to glycine because this requires alanine, and we're seeing a depletion in alanine. By the way, the reason why we see depletion in things like alanine, lactate, and pyruvate is because all of those are being shunted to produce glucose. So in the liver, where gluconeogenesis is happening, all of these intermediates are needed to convert the other direction to produce glucose. And so you have a depletion of all of those because the liver is it's not in a energy repleted state. It's using the fuel that it has and shifting all of it into glucose and then releasing that glucose. So because of that lack of alanine, you have less conversion of glyoxalate to glycine. Because of the decreased pyruvate, you have less activity of lactate dehydrogenase converting pyruvate to lactate. Instead, it's all being converted toward glucose the other direction. And that means that you have more lactate dehydrogenase available to convert the glyoxalate to oxalate. So that's one other mechanism. Then the other thing they talk about is that there's an increased conversion from glycolate to glyoxalate. And that's also because of a lack of lactate. Again, the lactate being shunted toward glucose, and the lactate has an inhibitory effect on the enzyme converting glycolate to glyoxalate. So when you have a lack of lactate, it helps or increases the availability of glyoxalate through that mechanism as well. So a few different mechanisms all going in the same direction here, leading to increased glyoxalate production when you have increased gluconeogenesis and increased glucagon. All right. So there's really one kind of larger category that we're going to go through briefly here that's important to touch on, which is the impact of different vitamins and minerals on oxalate metabolism, or the metabolism into oxalates and conversion away and all of that. And there's really only three primary nutrients we're going to focus on here. There are some others involved that we'll discuss later, but the primary ones being vitamin B6, which, as we mentioned, is primarily needed for AGT, that AGT enzyme. So if you don't have enough B6, that's going to lead to a lack of that AGT function, and you're not going to be converting that glyoxalate to glycine. You're going to have more available to convert to oxalate. The next one is vitamin B1, thiamine, which we touched on this a little bit in those earlier graphics. It's worth noting a couple of things. First is that B1 itself is actually needed to activate B6 to allow for B6 to be properly used. So if you have a lack of B1, that can also cause a relative B6 deficiency. Even if you have enough B6 available, it won't be able to actually be active.
Used appropriately.
Yeah, exactly. So B1 is important from that standpoint. And then, of course, B1 is also important in a number of different enzymes, as thiamine pyrophosphate, which is something that allows for various enzymes to function. So we're going to touch on that very quickly here, briefly here. The first study being one that we grabbed that figure from earlier, which is titled Oxalate Metabolism in Thiamine Deficient Rats. And again, this touches on the impact of a lack of B1 on oxalate production. And they state male weanling rats were maintained on a thiamine deficient diet for 4 weeks and compared with ad libitum and parafed controls. The decarboxylation of glyoxalate, both via the glyoxalate oxidation cycle and the alpha ketoglutarate glyoxalate carboligase, was significantly lower in liver and kidney mitochondria, leading to the accumulation of glyoxalate in the tissues and its excretion in the urine. Part of the accumulated glyoxalate is converted to oxalate, causing hyperoxaluria. So the important points that they mention here are that with thiamine deficiency, there's increased levels of glyoxalate and increased levels of oxalate. And again, in that pathway that we had looked at earlier, there's a couple different places where thiamine in particular is important. One is with the alpha-ketoglutarate carboligase enzyme, which helps, again, to clear glyoxalate and have less available to convert to oxalate. And then indirectly, this is not as, again, these aren't thiamine dependent, the aldolase enzyme and the alpha-ketoglutarate dehydrogenase enzyme, but they mentioned that with the buildup of glyoxalate, it actually impairs those enzymes. And so it will reduce the pathway of the glyoxalate oxidation cycle. And then, of course, we also know with thiamine deficiency, you're going to have impaired respiration, impaired TCA cycle activity and all of that, which is also going to lead to impaired alpha-ketoglutarate dehydrogenase activity, which is also needed for that glyoxalate oxidation cycle.
And something to add here, and it's not in this graphic, but say you don't have enough thiamine, right? And say now you can't activate the enzyme pyruvate dehydrogenase. Well, what then happens? The intermediate, the metabolites prior to entering pyruvate dehydrogenase, which are all the glycolytic metabolites, start to back up. And what do we talk about was a major driver of glyoxal production was dysregulated glycolysis. So if it's not only can you not get rid of glyoxalate, or potentially not only get rid of glyoxalate, if you don't have enough thiamine, if you create a thiamine deficiency, you may create a circumstance where you actually drive increased amounts of glyoxal. And something that's interesting to see, and we don't have the study here listed, but there are studies showing that benfotiamine, which is a fat-soluble thiamine derivative, can help to actually lower hemoglobin A1C values and glycation in the body. And part of that is through improving glycolysis. So just an interesting perspective here that there's, again, multiple ways in which not having adequate amounts of thiamine by itself can create metabolic issues that can lead to increased amounts of oxalate, or at least glyoxalate with conversion to oxalate inside the body. And another thing I just wanted to mention here, just to highlight how important vitamin B6 is to AGXT enzyme, they actually trial in primary hyperoxaluria, the genetic disease, they trial giving people high doses of vitamin B6 to see if they can optimize whatever function is left in that enzyme in those individuals. Because for a small portion of them, if they hyperdose vitamin B6, they are actually able to help minimize the amount of oxalate that they produce. Now, that doesn't happen for all people with primary hyperoxaluria 1, but it's just goes to show how important vitamin B6 is for that enzyme, and also how important that enzyme is overall, because just blocking the AGXT1 enzyme leads to massive hyperoxaluria with huge kidney damage and tons of tissue damage and things like this. So you really want to make sure that enzyme is working well and functioning well, and that's vitamin B6 is absolutely essential for that. And then obviously vitamin B1 is essential for vitamin B6.
Right. Yeah, absolutely. And it is worth mentioning there because it really speaks to how impactful vitamin B6 is and the AGT enzyme. Of course, there were a couple other things not mentioned by the study. One is the glyoxalate carboligase pathway, which converts glyoxalate to eventually to formate. And that was that one that we showed in this figure prior. But then also there's the impact of thiamine, as you said, on kind of other enzymes in terms of glucose metabolism that ends up having a direct effect on glutathione as well as NADPH availability, both of which are important for various enzymes that lead to less or more glyoxal and glyoxalate production. And so in this study, they touch on that. It's titled Toxicity of Glyoxals, Role of Oxidative Stress, Metabolic Detoxification, and Thiamine Deficiency. And they state glyoxal cytotoxicity was prevented by increasing glyoxal metabolism with thiamine or NADPH generators and was increased in glutathione or thiamine deficient hepatocytes. So what they're pointing to here again is excess glyoxal levels being a precursor to glyoxalate being increased if there's a lack of thiamine. And and that can be reversed if you provide the thiamine or if you provide NADPH, and if you, presumably if you provide glutathione, or if there's a lack of glutathione, it also contributes here. And they then talk about a couple of the reasons through which thiamine could be directly tied to these, basically in that it affects NADPH production via different enzymes in the pentose phosphate pathway, and then it also has effects on glutathione production. And then these things can affect glyoxal buildup, and then also if there's a lack of glutathione, there's a lack of glyoxalase activity, which causes that glyoxal to be favored in terms of the conversion to glyoxalate. And then, of course, also if there's a lack of thiamine, you're not going to have properly functioning mitochondria, metabolic function, oxidative metabolism, and that's also going to lead to increased reactive oxygen species, oxidative stress, and deplete glutathione. And they touch on that a little bit here where they state thiamine in its diphosphate form is an important coenzyme for transketolase, pyruvate dehydrogenase, and alpha-oxoglutarate dehydrogenase, and the branched chain alpha-oxoacid dehydrogenase complex, enzymes that are involved in the pentose phosphate pathway and citric acid cycle energy production. Thiamine also increased erythrocyte transketolase activity and decreased methylglyoxal accumulation when erythrocytes were incubated with 50 millimoles of glucose. So again, they're just kind of digging into the details of some of those pathways, some specific enzymes that thiamine is involved with that allows for basically proper antioxidant production and helps to protect against that oxidative stress that we know is a primary contributor here and helps to convert things away from glyoxalate.
Well, the thiamine is absolutely essential because the pentose phosphate pathway, which they're saying is completely dependent, like the enzymes are completely dependent upon thiamine. The pentose phosphate pathway is what's creating the glutathione and what's creating the NADPH, which is going to take the glyoxal and the glyoxalate and convert them to glycolate. So if you don't have adequate amounts of thiamine present, then you're going to wind up running into a circumstance where you won't have adequate glutathione, you won't have adequate NADPH, and you're going to increase the amount of glyoxal you have, because you can't convert away from it. Plus, you're probably going to increase production through having impaired or altered metabolism through glycolysis. So basically, the whole context of this, just to wrap it up or put a bow on it, is that if you don't have adequate thiamine, you'll increase the amount of glyoxal and potentially the increased amount of glyoxalate, which is the main precursor for oxalate synthesis. So a thiamine deficiency by itself can raise oxalate levels and also the precursor to oxalate, glyoxalate, and impair the metabolism of glyoxalate away from oxalate by changing the metabolism or function of multiple different enzymes and also the metabolism across the body at large. So it just goes to show how, again, so it's not just how much oxalates are you having in your diet, it's what's your thiamine status, how much vitamin B6 do you have on board, what's your metabolic state. All of these things start to become absolutely essential when you're trying to determine if somebody, why is somebody having an issue with oxalates? And then also, is the issue actually the oxalate, or is the issue the underlying context and metabolic state? And I guess to put this into further context, at least with the clients that I've worked with, I've had people say, oh, I have problems with oxalates. And then we start to change things, adjust nutrient status, change up the diet, improve different components. And it's oh yeah, I can tolerate, chocolate now. It's not that big of a deal. Whereas, when they initially came, I was I can't have chocolate at all. I can't have this. I can't have that. And they're thinking it's an oxalate problem. It's maybe, but is it more of a metabolism problem? And I think that in a lot of circumstances, these are metabolism problems that we're seeing with people, not necessarily issues with their, with oxalates by themselves in a vacuum.
Mm-hmm. Right. The question is, why is it an oxalate problem? Is it because we're not digesting fat well and we have intestinal permeability and our liver is stressed and on and on and on? So yeah, exactly. Very important points to highlight for sure. And obviously, as we're getting at, when it comes to metabolic function, there's tons of nutrients involved. I mean, pretty much every B vitamin, vitamin E. I mean, there's magnesium, zinc, so many things are involved here. So we're, of course, not touching on every single vitamin and mineral that's involved here, but of course, everything is important when we're, if we want to talk about thyroid hormone production and other things that affects liver function. I mean, there's tons of different factors, but of course, we're just trying to highlight mostly the nutrients that are intimately involved with oxalate metabolism. And the last one to mention here is zinc, which is important for a number of reasons, but one of them is the glyoxalase enzymes. And they mention that here in this study titled Molecular Enzymology of the Glyoxalase System, where they state that glyoxalase 1 and glyoxalase 2 are metalloenzymes, and zinc plays an essential role in their diverse catalytic mechanisms. So, those being really integral to making sure that the glyoxal that is produced, obviously we want to minimize that, but the amount that is produced is being converted toward the glycolate, not toward glyoxalate and then oxalate. So yeah, those are just some of the really specific nutrients that are involved in some of these enzymes. And again, I think we've really zoomed out quite a bit and talked about why it was important to go through these pathways and how they relate to general metabolic function, the things we talk about all the time, everything from sleep to digestion to liver function, obviously the macronutrients we're consuming. And we'll focus on that a bit more in the next episode, where we'll talk about how much oxalate the kidneys can actually clear, and the generally pervade idea that they can only clear 50 milligrams and anything above that is an issue. So we'll talk about that and all the different things that can affect the kidneys' clearance of oxalates. And then we'll also talk about many of the mechanisms, because we touched on just one today, really, as far as how a low carb and or carnivore diet could increase oxalate production. But there's a number of other reasons, a number of other things that could tie low carb diets and carnivore diets to excess oxalate production. So we'll dig into all that in the next episode, and also the impact of sugar, glucose, and fructose, and whether or not those are actually concerns when it comes to oxalate production. So with that, Mike, would you like to share where the listeners can find more of your work?
They can find me here on Energy Balance Podcast. And they can also find me on my YouTube channel, Mike Fave, as well as my website, mikefave.com.
Awesome. Well, if you guys did enjoy that episode, please leave a like or comment if you're watching on YouTube. If you're listening elsewhere, please leave a review and 5-star rating. All of those things do a lot to help support the podcast and are very much appreciated. As always, to check out the show notes where I'll link to the studies, articles, and anything else that we referenced throughout today's episode, head over to jfeldmanwellness.com/podcast. And if you are looking to optimally support your metabolism and maybe clear out these kind of chronic oxalate issues, or maybe you're looking to lose weight, improve your digestion, get amazing sleep, rebalance your hormones, boost your energy, and so much more with clear action steps and strategies alongside personalized guidance from me, then head over to jfeldmanwellness.com/solution, where you can find all of the information for the Energy Balance Solution program. This program includes customized health coaching. It includes a video library with videos on how to regulate blood sugar, how to restore gut health, how to lose weight without destroying your metabolism, how to boost your metabolism, how to get amazing sleep, and tons more. There's also resources like a sample meal plan, recipes, a supplement guide, many other resources in there, and also a private community. So head over to jfeldmanwellness.com/solution to check out all the details. And with that, I'll see you in the next episode.